Good evening, and a warm welcome to the Oxford University Scientific Society in 2021. My name is Luna, and I am the newly appointed president of the OESS. Together with the newly elected Vice President Carlos, as well as the rest of the OESS committee, we have put together a fantastic lineup of 8 speakers for this Hillary term, featuring artists, professors, popular science book authors from all over the world. I'm sure it will be a treat for everyone. To kick off, we have invited back one of our old friends, Professor Wade Allison, to give a talk on nuclear energy and climate change. If you have questions for Professor Allison, please write them in the comments section. Our diligent committee members will collect and present them to Professor Allison and me after the presentation. With that, let's welcome Professor Allison.
In this talk, I want to confront the current intuitive responses to the climate change problem with the hard facts of natural science. This past year has reminded us, everybody, that science is essential to our survival. Like COVID, climate change affects everybody and needs global policies that command global acceptance to optimize social and economic stability. But unlike COVID, there is no vaccine. To avoid disaster when changes occur, the provision of essential goods should be reliable and resilient. Among such goods, access to energy has always been critical. To secure energy, life has taken several momentous steps forward in the last 3 billion years. Let's begin by understanding those steps. Early plant life took energy from sunshine, and when that was not available, it died off until the next season. A great step forward came when some life forms became mobile by evolving an individual secondary energy store provided by a stomach to digest food. Along with fish, birds, and other animals, this squirrel knows all about that. Life for him is about nuts. Can I have the second slide, please? The energy density of nuts, that is about 23 megajoules per kilogram. Other foods are similar. Can I have the second slide, please? Other foods are similar, as many human Weight Watchers know. It's printed on the packet. But broadening the understanding of energy density is now essential if the right public policy decisions.
Sorry to quickly interrupt. Professor, you want to change your slides by clicking on your screen? If that is, there we go.
Well, I will go back to the squirrel. Can't miss out on the squirrel. He knows about energy. There. So we need more nuts. To broadening the understanding of energy density is now essential if the right public policy decisions are to be made in response to climate change. The next step in the story of life and energy came about 600,000 years ago, perhaps, when mankind used his newfound intelligence to find a way around the limited energy capacity of his digestive system. First, he secured external energy by organizing teams of horses, oxen, and slaves. No other animal had done such a thing before on such a significant scale. Then he learnt to use the energy of wind and water and biofuels and fire. No doubt, as in this picture, there were understandable safety concerns amongst the environmentalists of the day, but the extra warmth and cooked food won them over. They built great empires, sailed the seven seas, refined metals, and laid the foundations of education, mathematics, and astronomy. Nevertheless, life was short and wretched, health poor, and the population small. Justice and human rights were for the few. Sport and vacations were rare. The next great step forward came with the Industrial Revolution. Suddenly, huge amounts of energy became available anytime and anywhere. For 200 years, the politics and economics of the world were determined by who did and who did not have access to coal, oil, and gas. Vast technologies were built on these new fuels. Life expectancy doubled, the population quadrupled, health, sports, vacations, arts, human rights flourished. But without carbon fuels, these benefits can no longer be taken for granted. A couple of centuries earlier came the birth of natural science. Its governing influence on decision-making was summed up by Adam Smith, the great Scottish economist. Science is the great antidote to the poison of enthusiasm and superstition. The popular hope that somebody else will invent something is ill-advised. Any idea that does not conform with the scientific laws of energy will not work. The two most important laws of energy are that energy is conserved, you cannot make it or get rid of it, only change its form and move it about. And the second is that left to itself, energy tends to dissipate or run downhill. Both laws have been established for over 170 years. We have intuitive ideas of these. Who put that boulder at the top of the hill? How did it get there? And what has stopped it rolling down already? What heated my cup of coffee? And why hasn't it already gone cold? But be careful. Touchy-feely ideas of energy can be very deceptive. Tingles are in the mind only. The need is for fuel, an energy store with high density that is stable and can be controlled as required. On a large scale, such fuel is very rare and its stability is a constant concern. Let's start with what is familiar, food, like the squirrel. The human body burns a few watts per kilogram. That is the metabolic rate. Our food energy requires about 8 megajoules. A modern man needs far more energy, about 400 megajoules per day, 50 times as great. That's the UK figure. The control and stability of stored energy is crucial, especially where energy release can be spread by chain reaction, as in fire. Uncontrolled energy release really is frightening. What can we say about fuels and their limitations? A complete scientific search for all kinds of energy finds 4 distinct classes of fuel. The adoption of the first 2 triggered major revolutions in human civilization. The question is, now, where do we go from here? First, the energy that we can feel. The first class of energy, these sources are have familiarity, even although they appear rather different. Moving or falling objects, water, wind or sunshine, the things that we talk about every day when we talk about energy. To compare these sources, we need to be able to measure them, and the numbers really matter. The energy of a falling object from height h is GH joules per kilogram. I hope anybody looking to get a place in Oxford would be able to get that from their A-level syllabus. At 100 meters height, that energy is 981 joules per kilogram, whatever the object. Let's call it 1 kilojoule per kilogram. Similarly, for any mass moving with velocity v, the energy density is a half v squared, whatever the mass. At 10 meters per second, that is 50 joules per kilogram of moving stuff, water wave, wind, or a moving car. So 0.05 kilojoules per kilogram. For wind, with air density 1.2 kilograms per cubic meter, rho v is the number of kilograms of air reaching a square meter of the turbine per second. So the power available per square meter of swept area is a half rho v cubed, which at 10 meters per second is 600 watts per square meter. Note that third power. Similar to the average solar power, which is about 300 watts per square meter. So the actual power delivered, of course, the actual power delivered will be less, cannot be more, whatever the technology and its efficiency. If we want the intuitive comfort of energy that we can touch and see, that is about the limit. These are the renewables, and that's why people like them. Higher speeds or heights are not so easy to find and not always safe. A maximum, perhaps, is the molecules in a gas moving at about the velocity of sound, say 300 meters per second. So they have an energy density of about 50 kilojoules per kilogram. First, these figures are tiny compared with the energy density of the squirrel's nuts, or even of the Jaffa cake that was sitting on my desk as I wrote this. That has about 16 megajoules per kilogram, and it's printed on the packet. For the nuts, that's 23,000 times the energy density of the water behind the 100-meter high dam that made our nerves tingle. Evidently, our nervous intuition is a poor judgment of energy. We call the energy of food chemical. But where is the clockwork? Chemical is just a name. Other phenomena in use today are equally strange to the intuition. In an electrical circuit, electrons go through a solid copper wire as if it was a hollow pipe. How come? Evidently, our natural intuition is easily confused. This was all first understood in the 1920s as the wave theory of all matter. Chemical energy is the kinetic energy of wave-like electrons trapped in atoms, otherwise known as Fermi energy. And we will show that in a simple calculation that I'll show in a minute. Quantum mechanics is universal, but becomes most evident when the scale is very small. Everything is made of atoms, 10 to the minus 10 times smaller than us, and within every atom has a nucleus 100,000 times smaller again. So whereas quantum mechanics is dominant for electrons in atoms, it becomes overwhelming for electrons and protons inside nuclei. Well, let's take a break from this heavy science and look at a photograph that was taken of me and 3 colleagues at a meeting in Warsaw in September 2019. And an extraordinary coincidence, well, perhaps not, on the wall behind my head, marked by the red arrow, hangs a copy of a very famous picture of those who established the quantum mechanics nearly a century ago. 17 of the 29 attendees of this 1927 conference won the Nobel Prize. Mary Curie in physics, you can see her sitting there 2 away from Einstein, 2 to the left of Einstein. Mary Curie in physics and in chemistry, though is best known today for her work in the 3rd subject of medicine. The other figures, all men, include Einstein, Dirac, Schrödinger, Heisenberg, Planck, de Broglie, Bohr, Pauli. Indeed, only Rutherford and Fermi, of the great minds of the first half of the 20th century, do not appear in this photograph. Just one slide of heavier algebra, and then we can find its consequences. Look at the sketch of the wave and electron in an atom of size L. To fit in, the wavelength cannot be much longer than 2L, and in quantum mechanics, the momentum is related to the wavelength by h over mv. So for its kinetic energy, half mv squared cannot be less than h squared over 8ml squared. Of course, proper 3D calculations are a little bit different, but not much. Putting in values for h, a constant, m, the mass of the electron, and L, the size of atoms, gives this kinetic energy. The same energy scale for chemistry, electronics, batteries, laser, food, combustion, explosives, etc., all around a few volts per atom or a few megajoules per kilogram. But this very same calculation for nuclear, with L being 100,000 times smaller and M 2,000 times larger, gives another energy scale, 1,000,000 times larger than electronics and chemistry. This quantum clockwork is the same as the mechanism is the same as for chemistry, but this factor of 1,000,000 changed the course of history in 1945, and as a good energy store, it has been misunderstood by most of society until now. And that is what we've got to put right. A quick look through the data, and you can find the energy density of nuts, Jaffa cakes, and the Beirut bomb, and lithium-ion batteries, anything else you like, and they're all give or take molecular weights about similar of a few megajoules per kilogram. That includes batteries, of course. And that brings us to this table, which is essentially the scorecard that this whole lecture is about. There are 3 columns here with 3 vastly different scales of energy density. The first, the classical, familiar, touchy-feely, alias renewables. The second, the quantum electronic, also known as chemistry, 10,000 times larger, and most available on large scale in the form of fossil fuels. And thirdly, quantum nuclear, 1,000,000 times larger again, whose primary source is uranium and thorium. More about that in a minute. Their adoption is related, the adoption of each column in the history of man has been related to successive revolutions in civilization. First, the pre-industrial revolution that gave man supremacy over all other creatures. Second, the industrial revolution of carbon fuels, steam, chemistry, and electronics. If use of carbon fuels is to reach net zero, should we build the future of our civilization on nuclear? Note that nuclear fuel needed per head is about 1 kilogram for life, 10,000 million times less than renewables. But where do these energies come from? Renewables are renewed by sunshine and the weather sometimes, if it's not raining and the sun is shining. Fossil fuels were primed by solar photosynthesis billions of years ago and then stored in the ground. But where did the nuclear energy come from? What put its boulders at the top of that hill? Exceptional gravitational collapse can deliver an energy density even greater than nuclear. That is the 4th distinct class of energy, which fortunately is not available on Earth today because it would blow everything to pieces. In supernova and similar explosions before the Earth was formed, all the elements heavier than iron were created, including the still surviving unstable uranium and thorium. These phenomena are seen today elsewhere in the universe, such as here in the Crab pulsar that was seen in 1054. And then there's the recently discovered black hole events, where they're also being produced. Some people imagine that a different energy source could turn up, but they should look at the science. That is not going to happen. Hydrogen, batteries, these have their places, but they are not large-scale primary fuels. They're secondary. If it's not carbon, it has to be renewables or nuclear. So let's go back and look at renewables again. What is wrong with large-scale reliance on daily and seasonal renewables? The media, politicians, and energy gurus think that is the answer. But technology is not natural science. Spending money on energy solutions when the energy is not there ends in tears. Energy for pre-industrial humans was always at the whim of seasons and weather. Renewable, but often not renewed, always unreliable and weak. That is why the mills of northern England gave up water and wind and welcomed coal and steam as soon as they could. How do renewables perform today? Let's look at wind. Wind farms offshore are said to be 37% effective and onshore about 22% effective. Here is a plot of the actual wind energy output for 2018 from the Wind Europe report. It shows that on the 8th of December, they actually achieved an average 50% of their installed capacity. Why is this performance so poor? The maximum wind power goes as V cubed, as we've just seen. So the considerable variation in wind speed causes a much greater variation in wind power. If designed for 30 miles an hour, at 15 miles an hour, the power output drops to 12%, an eighth. At 55 miles an hour, turbines are shut down to avoid destruction. So the fossil fuel industry stands by to satisfy the missing 65 and 75% of demand. It is an open secret that the oil and gas industry has its eye firmly on the slice of cake, this slice of cake, but that cannot lead to zero carbon. So we should not buy that argument. Today, thanks to the internet, you can, and everybody should, watch the consumption and generation of electricity in different countries around the world. Here on the 24th of 2020, there was no wind and no solar, as you can see on the bar chart on the left-hand side, where there's only a tiny little bar for solar and a negligible one from wind, and a huge red one for gas. As usual, nuclear was steady, and so was biofuels, but that is at the destruction of that's wood. As usual, there was a large import of 4 gigawatts from the EU. That is bigger than Hinkley Point C. Why does nobody ever seem to notice it? Otherwise, the source was gas. Is the public happy to rely on gas? Some from the North Sea, but also USA, Russia, and the Middle East. Not exactly resilient and local and secure. On the 5th and 6th of December, sorry, I've got my... On the 5th and 6th of December of 2020, the wind failure was so bad, as shown on this slightly different display. You could see the wind there was 0.67% of the production, and the wholesale price of electricity rose to over £350 per megawatt hour, as shown in the display at the bottom. The instability of the renewable supply also goes the other way. Here is the electricity map display for Germany of the 5th of April. Unwanted electricity prices drive, the energy has to go somewhere, and it is difficult to dump energy. And in fact, the price here went to minus 50 euros per megawatt hour. People were paid to take it away. How about energy storage? Big subject that everybody likes to talk about in the newspapers is storing energy and the need for big batteries. And Mr. Musk makes a lot of money from it. And a battery, of course, is nothing more than an energy store. To bridge a loss of UK grid power for a day would require 1 terawatt hour. That is 3,600 terajoules. At the energy density of a lithium battery of 1 megajoule per kilogram, that would require 3.6 million tons of lithium batteries. Such stored energy, equivalent to, not just equivalent to, equal to 1,000 and more size the bombs that went off in Beirut this last year, or readily electrically wired. In fact, a battery is a bomb that can deliver energy very quickly. Everybody, including Musk, should learn about this. Batteries, beware what you wish for. In this Korean report, the authorities apparently do not understand why 20 large energy storage fires occurred last year. We may expect that many more battery fires like this will occur, and advances in battery technology are limited by the periodic table. Having moved from a lead-acid battery to a lithium battery, you cannot improve much, but don't expect a big improvement, and if they were, they would be even more dangerous. Because renewable energy is so dilute, its power plant has to be huge to harvest the power required, even under the best conditions. When steam came 200 years ago, hydro, they gave up their trying to use water power. Hydro is dangerous with a high mortality for dam collapse. It's not environmental. 1.3 million people were relocated in the construction of the Three Gorges Dam project, and the lake is 600 kilometers long. By contrast, a 1 gigawatt electric nuclear plant takes only 15 hectares of land. More than 100 times as much land is needed for a plant that works in the daytime intermittently, depending on the weather. I'm talking about solar now. Vast areas of nature are desecrated in the name of green. This is a meadow, so-called, near Abingdon. William Wordsworth would weep. He would be appalled. What has happened to the environmentalists? But there's worse. Because renewable plants are so large, particularly wind and solar, they are easily trashed by exceptional weather conditions. And these, of course, are becoming more frequent. They're equally easily sabotaged. So what are we to say about renewables? They are not fit for purpose. They don't last very long, about 20 years or so, in contrast to nuclear and hydro, and I've got some more information on that, which came in this afternoon, and I'll show you that later. So if we're to abandon carbon fuels and avoid renewables, what about nuclear? The only problem is that people do not understand and turn away, especially the media and short-term businesses. People's education failed them. School taught them nothing about nuclear. It confused the science of nature with the human competition that is technology. In the Cold War, the public clamor for protection against nuclear weapons persuaded politicians to appease concerns with draconian radiation regulations suggested by an international United Nations committee. However, these remain totally unsupported by any scientific evidence to this day, although the international bureaucracy that oversees this advice is not willing to recommend an end to its authority. They never do. It's their livelihood. Earlier, I quoted Adam Smith, quoting that science should overcome collective fear and excitement. Well, in the case of nuclear energy, it has failed so far. People think it is dangerous, but in fact it is not. To understand and put things in perspective, there are two well-established medical effects which one should understand. The first is the placebo effect, when a diseased person is told that they've been treated and their health actually does improve. And this is why all tests, both of the vaccines, for instance, have to be blind, so that it's not known whether you have actually been treated or not. There's an equivalent to the placebo effect, where you tell people who are in fact perfectly healthy that they've been injected or irradiated or cursed or something, and they fall ill and they will die. There are well-documented cases of this negative effect of suggestion. They're genuinely ill, but it's caused by psychological effects. This is what happened at Chernobyl and at Fukushima. It makes exciting TV drama, perhaps, but so do murder mysteries. But that doesn't mean to say that murder mysteries happen frequently in real life either. This is a slide taken from a conference that I went to with some people from Fukushima, social workers, who explained the ghastly things that happen when people lose confidence in one another, in authorities, in science, and in the future. At Fukushima, nobody got a significant dose of radiation, and nobody has died, nor will they do so, from the radiation. However, the authorities had no knowledge, no plan. They panicked and they evacuated a wide area. The public knew nothing, lost trust in the authorities and in science and in their own safety. This had a very serious effect on social and mental health, leading to alcoholism, family breakup, bedwetting, and all the rest of it. So fear and dislocation, especially for old people, caused at least 1,600 deaths, but none of them was caused by radiation. At Chernobyl, where there were 28 early non-cancer genuine radiation deaths and 15 fatal cases of child thyroid cancer, the UN report of 2006 reported widespread hopelessness, mental and social health cases. In the case of entertainment videos and books, these are associated with the radiation. However, to avoid the distortion by the nocebo effect, the effects of radiation must be studied with subjects that are unaware of the fact that they have been irradiated. Such data comes from experiments with animals, with humans who live and always have in high radiation zones, and therapy patients who welcome high doses for their own health in hospitals. In particular, we may look at the wild animals in the evacuation zone at Chernobyl. They were not evacuated at short notice. They were not told that their lives were at risk. They were not paid large sums in compensation or encouraged to watch sensational videos. but BBC, National Geographic and Discovery Channel wildlife programs have shown that they are thriving in the zone freed from human interference. Evidently, low and moderate doses of radiation are harmless. How could that possibly be? Nuclear radiation is the most powerful agent known, and the international political and military powers of the last 70 years have wielded influence on that basis. Nevertheless, the natural safety of nuclear technology is second to none for two distinct reasons, one secured by physics and the other by biology. In physics imposes nuclear self-distancing. Nuclei are kept apart by universal electrical barriers of several million volts. Even at the temperature of the sun, nuclei only meet one another once in a few billion years. Otherwise, no two nuclei ever meet, and so they do not discharge their nuclear energy. The only exception to that is the neutron, which can cheat its way through the electrical barrier. But the neutron is unstable and self-destructs in a few minutes. Otherwise, radiation from the decay of leftover radioactivity is the only evidence of nuclear activity, which is why it wasn't even discovered until the end of the 19th century. Furthermore, radioactivity cannot spread like fire or an infection. It only affects the nuclei that are decaying. So much for physics. What about biology? A completely different argument. To defend against attack by biological life can be disrupted by chemical energies, by the energies of nuclear radiation can be 1,000,000 times greater. You might expect that life would lose this unequal fight. If that were true, we shouldn't be here today, especially as the radiation levels, natural radiation levels, were much higher in the Earth's history than they are today. The whole design of the biology of life was evolved to survive attack by radiation and oxygen and their physical environment and other organisms. Indeed, attempts by the human brain at large to micromanage radiation protection is precisely the problem that we face. The animals are better off in this respect. Their lives are protected by nature, undeterred by Geiger counters that they don't need. But we need constant reassurance on this from all points of view, most particularly from the contribution of Mary Curie, who wrote, "Nothing in life is to be feared, it is only to be understood." In spite of the messages of fear and excitement from the media and regulators, the public willingly accept the benefit of radiation for their own health. Mary Curie is one of the most popular names in medical charity. Why do the public accept one standard for their own health, but demand a different one for the environment? Well, they don't. It's what they were told. In fact, in 1934, the safety advice was set internationally. Since 1934, the safety advice was increased 700 times higher than it was today. So now what we need is a widespread, radically new program of public education and school teaching about nuclear. The Japanese, people think you can't do that. It's not true. The Japanese themselves do that successfully about earthquakes and tsunamis, such that despite 18,800 deaths from the tsunami, society is able to recover from the effects of the earthquake and tsunami. But they don't do it for radiation, so that society is unstable and unable to cope, even for an accident, with no deaths at all. So what should we do now? We have a big program. There are several 20-year objectives which need to be followed. First, we need to invest in new borderless education worldwide, that all may understand more about nature without the prejudice of specialization. By what I mean is, if your education teaches you to be an engine driver, you don't ever want to step outside the confines of what you've learned as an engine driver. What we should be doing is adhering more to the 18th century model of where education was broad, so that we were not trapped in specializations which we happen to think we know about. Secondly, we need, in parallel with that, we need to develop nuclear technology. This is happening. There are many, many designs of new nuclear reactors which are ready to come to market in the next 5, 10, 15 years. And we need to make it available for the common good worldwide. Not, I said, for the common good, not to make America great again or to make anybody else great again, but like the virus, like the vaccines, they need to be for the common good. We need to reform the regulations. They go right the way up to the United Nations, but they need to be made to match with the scientific evidence, which they don't. And finally, we need to plan for resilient, secure, local nuclear energy hubs. I mean that for towns like Oxford and Reading or something, with 100, 200,000 people, with a nuclear power station where the nuclear power station runs continuously and provides heat and electricity, and off-peak, which is quite a lot of the time, it provides hydrogen for homes and industry, and it provides chemicals and transport and indoor farming. I don't know if the people are aware of the advances that are being made. Given the heat and LEDs that you can run from a nuclear power station, you can produce food inside, free of season, free of daylight, free of geography, all the year round. That would be a wonderful thing to look forward to, and could all be much healthier. Just to explain what I mean, a steady nuclear power output like the blue line would be able to accommodate fluctuating electrical demand, and as it goes up and down, to produce hydrogen, desalination, and short-term storage on the side. This has been proposed in Scandinavia by a number of people. And just today, this afternoon, just a piece of late news, as we speak, there is a conference going on at the Nuclear Regulatory Commission, Thursday, that's today, about allowing the possibility, not of all nuclear power stations, but allowing them to apply for 100-year licenses, subject, of course, to all the usual constraints. But that sort of thing has not been thought of before. It is 4 to 5 times the time for lifetime of of a renewable. Well, we've got to questions and answers, and I'll hand over and we'll find out about that in a moment. Of course, I've been working on this for a considerable number of years. I've written 2 books, and they're both available in hard copy, or you can find the PDFs online at these links. But perhaps we should now go to the Q&A.
Well, thank you very much for your talk. I am pleased to see our audience interacting with each other alongside Professor Allison's talk. Now we'll turn to questions from the audience. May we have the first question displayed as a caption, editor? Right? Nope, don't worry about that. Our editor will handle the technicalities.
Do the wrong thing.
All right. I think our technical officer has been saying there's some problems, so I'll just read one out. I'll read a short one. Actually, this one is something I'm curious about. So what do you reckon that we should do to prevent accidents such as Fukushima or Chernobyl from happening again?
Well, first of all, Fukushima wasn't a very important accident. You can't say it's called a disaster. But can't have a disaster. Nobody was killed. There were disasters at the nearby oil refinery and gas stations which were burnt to the ground. The BBC correspondent, Rupert Wingfield Hayes in Japan, asked me today, he said, but there were 3 meltdowns. And I said, what do you think happens in a nuclear meltdown? It's not that disastrous. You get a mess. You get a mess when much bigger mess from the Horizon disaster or from an oil tanker going aground. So in a way, the new nuclear power stations won't be likely to fail can't fail the way that Chernobyl did. And Fukushima was a result of quite extraordinary seismic activity, which was much more dangerous than what happened at the power station. So I wouldn't worry about that.
All right. Okay. I can see questions flooding in from our audience.
Right.
We'll just go one by one. Okay. It seems to be that our editor has fixed the technical problem. So we'll go ahead with this one. Has an effective solution to the stocking and disposal of long-lived nuclear waste been found?
Let's look at the problem. I said that in your entire lifetime, you might use the product of 10 million tons of water going over 100-meter high dam, or 1,000 tons of coal, or 1 kilogram of uranium and thorium. 1 kilogram of uranium and thorium cannot make more than 1 kilogram of waste. So the first thing to understand about nuclear waste, there is very, very, very little of it. The second thing to understand is that nobody has died of nuclear waste. It just hasn't happened. No, it's nasty stuff and it needs to be disposed of properly. It can be buried, and I have offered in publications that they can come and bury it 200 or 300 meters under my house if they want. I wouldn't be bothered. So the nuclear waste problem is a fiction.
I suppose it might have been, we might have a little bit of a bias against anything to do with nuclear, as you have mentioned in your talk.
Yes. Well, it's not a bias, it's a fact that people don't know, because nobody's ever told them. And they've had reasons for not knowing. The oil industry has not wanted people to know about nuclear power, because that would harm their prospects. And the military and the international political have been happy with the stability that has, meta-stability that has come in the fear, secured by the fear between nations. But I don't think we want to go there.
Okay, I can see many different questions coming from the audience, so maybe have the next one, please. What do you think about companies like TerraPower designing small reactors for small-scale energy production?
I can tell you, I haven't talked at all about the design of the new nuclear reactors. The situation's rather like it was in about 1900. In about 1900, we were just getting rid of the chap who had to walk in front of the car waving a red flag because there was a dangerous motor vehicle coming. And at that point, when the law was changed, there were hundreds of designs of new cars being to go on the road. Some of them didn't last very long. Others were steam-driven and went back to an earlier technology, and they died out because they were a little unwieldy, but still, like Hinkley Point C and Sidewell C, they made a significant contribution in their time. And then there are cleverer ideas equivalent to petrol and diesel engines, if you like it, like TerraPower and Motex and other, Rolls-Royce. There are lots of them. And it's not, I think, for natural science to rule one out and the others in. Let the market decide which of these is in fact going to be the best for the job. We can't spot Henry Ford coming up along, but it's not going to be Elon Musk. We are looking for a new style Henry Ford nuclear Henry Ford coming out of all this. So it might be Bill Gates, but there are a lot of other contenders. Let's see what happens.
Indeed. Let the market decide. Spoken like a true economist here. Maybe have the next question, please. I know there are many of them. How can nuclear industry and groups like anti-nuclear campaigners work together for a brighter future?
How can it what them?
How can the nuclear industry and anti-nuclear campaigners work together?
Well, I think it's all about talking and explaining and answering to me and arguing with me about what I've said and listening, not just taking what people are told without asking questions about it. So I think people aren't so stupid, but if they think, you see, nuclear is thought by some to be academically terribly difficult. And you've got to be a brain box in a white coat and pebble glasses to understand it. And therefore people were turned off. Now that is very bad education. And I hope that's not the Oxford way of doing things. You've got to find out. In fact, I can't remember her name, the inventor of the Oxford vaccine was saying of science, you've got to go and find out. That's what we've got to do. So it's a matter of education. People from my generation are probably a lost cause. What we've got to worry about are the younger people, people who are thinking of investing their careers in the nuclear industry and their friends and colleagues that they come into contact with. And it's those arguments in pubs, when they're allowed to have them, it's those arguments and discussions which is where the problem has to be solved.
I see. I think it really comes back to the point that we're scared of the things that we don't know enough about.
Yeah.
And the fact that we're not being told enough about nuclear energy and how much potential it has really does harm its future. Could we have the next question? Is transmutation of nuclear waste an option to reduce the half-life of particularly long-lived nuclear wastes?
Well, I don't call it transmutation. What I would call it is that nuclear waste, in fact, for well-defined physical chemical reasons, is only ever about in a normal today's reactors only about 2% used. So there's an enormous amount of unfissioned energy still in there. So several of the new nuclear reactor designs actually are designed to burn. You don't call it transmute. They're actually for building power stations, which are going to use the nuclear waste to create more energy. When the nuclei that are actually fissioned have a rather short lifetime, typically less than 30 years, so they're all gone in about 600. And that's not really a problem. So yes, you can burn it up, but I wouldn't use the word transmutation. That suggests you're solving a problem. I would say you should be exploiting the fact that the waste is only half you. Well, only 2-3% used fuel.
I guess that's also shows the importance of better technology. I think we have time for about 2 or maybe 3 more questions. So could we have the next one, please? Is nuclear contamination less fatal than we think? I mean, coming from a biologist's point of view, we get told that if you're exposed to too much radiation, you get cancer. I don't know what you would like to think about this problem.
Well, I'm a physicist, and I've spent the last 15 years since I started on this particular thing, learning a lot of biology, and I gave for many years, gave the medical physics lectures in the physics department. And so I followed it up very carefully with doctors and so on. Nuclear radiation is a very bad, inefficient way of causing cancer. Cancer is much more likely to be caused by oxygen, which leaks out of the out into the trying to remember in the cells, the energy producing subcells in the cell in oxygen is much more likely to be caused by that. And there are experiments. I could show you the data where if you take dogs, well, you can do it with mice, but mice don't live very long, so they're not very comparable with humans. But with dogs, you can feed dogs with radioactivity every day throughout their lives. How much radiation do you have to give them before their life is affected? Not only from cancer, but from anything else. And the answer is about 1,000 times as much as the normal regulations tell you to be frightened of. You can, of course, radio cancer therapy is killing cells. So you can kill cells with radiation, but it's in the large numbers of factors of 10 that you need to do that. So there's a big gap between causing a bit of cancer and what we're considering about in the environment. That is why 10 days after Fukushima, I actually managed to get a piece published in the BBC where I said that nobody was going to die, and they didn't. And it was perfectly obvious, but it was the bureaucracy was not happy to follow me for another couple of years later.
That's true. I suppose since I am partly a medic, we get told that in radiotherapy, you must focus different beams on the same part of your body to make sure that you do kill those cells. So it is actually not exactly harmful to the other cells that's just on its way.
Well, if you then I'd have lots more to tell you, But medicine will be a big beneficiary of getting this problem right, because the radiation doses that are used not only in therapy but in imaging could be, certainly in imaging, could be much higher without causing any harm. But the regulations prevent people getting the doses that they need for their health.
All right. As much as I would love to talk more about medicine, so since I'm partly a medic, I would love to have the next question. Are there any reliable estimates of the amount of uranium or thorium available on Earth?
Yeah, yes, there are. I mean, everything depends on the cost of uranium. So, in fact, one of the reasons why nuclear waste is not used at the moment is for in reactors is because it's actually there's no shortage of uranium in the ground, and it's just as easy to dig it out. So you can dig that out. There's uranium is soluble in seawater. So in fact, there's a very large amount of uranium in the sea, and that could be extracted, no problem. And then there's thorium, and there's 4 or 5 times as much thorium in the world as there is uranium. And the technology for using uranium in nuclear reactors also needs a bit of development, but there's no doubt about it, that will be done in 10 or 15 years, and that will be available. So on the timescale of 20 years, which is what we have to do to completely deal with net zero, we can expect thorium reactors, waste reactors, and all of these things. So fuel is not a problem. There are lots of different solutions.
I see. We'll have one last question, and then we'll conclude. What are the practicalities of thorium breeder reactors in comparison to uranium reactors? This one you will love. I can see it's about physics.
The good news is that all of thorium can be used as a nuclear fuel. It's all uranium, thorium-232. The problem is that it is you can't substitute immediately for your uranium. You've got to, if you were, as it were, like the match, you've got to start the fire with some uranium as well. And this technology is being developed. It will happen. I'm quite sure about that. Nobody's asked you about fusion. If they did, I would say that fusion is just over the hill there, and on this timescale of climate change, which is going to go on for centuries. Let's not fool ourselves. This is not something, climate change doesn't stop in 2050 or 2100. It's going on to go for hundreds of years. And hydrogen fusion will certainly contribute there. But there are a lot of technical problems to be solved before that will come online. But thorium will come before that.
All right. I believe that is all the time we have for questions. Professor Allison, you've definitely made me more hopeful about the prospects of nuclear energy. Thank you to all of those who made this talk possible, including our committee members, our sponsor Going Life, our editor Carlos, our audience, and especially Professor Wade Allison, who gave his precious time. Next week, on Monday evening, the Society will be having Professor Marcus du Sautoy, the Simoy Professor of Maths here at Oxford, talking about his new book, The Creativity Code, making the link between artificial intelligence and creativity. Follow our Facebook page or subscribe to our mailing list to receive updates. Again, thank you, Professor Allison, for the talk. We'll see you again on Monday. Enjoy the rest of your evening.